Hi, everybody. Welcome to the AOCS Student ePoster Pitch Competition for the Edible Applications Technology Division. My name is Jill Mosier, and I'll be moderating this session. And I would like to introduce our three judges. And hold on, I lost their names. Okay, sorry about that. Our three judges are Christina Luo, Tom Tiffany, and Super Team Gosh. Just to run through what we'll be doing today, there's going to be three competition finalists today. Unfortunately, the fourth finalist had to withdraw, so there would just be three. After each finalist will present their poster for 5 minutes. After each presentation, there will be 7-minute question and feedback session from the judges. The audience will be able to put their questions, if they have any, in the chat function of whichever application they're using to watch this competition. After all the presentations have ended, we'll pause the stream for a few minutes to allow for final judge deliberations, and we'll have time for the audience to also judge or vote for their favorite presenter. Lastly, we'll announce the first and second place winners of the AOCS Student ePoster Pitch Competition for the EAT division. So I want to wish everybody the best of luck and thank all of our judges and the audience for attending. I'm going to go ahead and announce our first presenter. Our first presenter is Fien De Witte from the Department of Food Technology at Ghent University in Belgium. And the title of the presentation is Determination of Solid Fat Content in Plain Fats and Suspensions with Lab Scale SAXS Device. Good luck, Fien.
These are pralines. We all know them, a soft and tasty filling surrounded by a layer of chocolate. Both the filling and the chocolate contain particles suspended in a continuous fat matrix and are therefore suspensions. Such a praline is just an example of a complex food product. If we want to analyze, for example, the hardness of the praline, we might find differences in hardness between the filling and the chocolate. This might come, for example, from the ingredients that we used, like, for example, the particles, but it might also be influenced by the solid fat content. The solid fat content, or the SFC, or the ratio of solid to total fat, is a property of a fat that is normally analyzed by low-resolution nuclear magnetic resonance, or NMR. The result of an NMR looks like a solid fat content curve as function of the temperature, as it is displayed below. At a low temperature, we have a high solid fat content, and when we increase the temperature, the solid fat content decreases. However, if we would like to measure the solid fat content of a suspension, we should make some adaptations to the NMR method, because of course our solid particles will also give a signal. On the other hand, I would like to propose small angle X-ray scattering, or SAXS. It is a technique that is often used to characterize distances in partially ordered materials. For example, if we would have a fat that is partially solid and partially liquid, for example, the blue curve at 10 degrees, we will have a distinct contribution of the solid part and a distinct contribution of the liquid part of the fat. When we increase the temperature, the solid contribution decreases and the liquid contribution increases. Therefore, SAXS might be a suitable technique to study the solid fat content. Moreover, in the SAXS region, normally the contribution of particles is very limited. If we want to study the solid fat content by using SAXS, we need two profiles of our sample. One profile can be obtained, for example, at the crystallization temperature, in this case 20 degrees Celsius. We will have a solid and a liquid contribution. If we then melt the sample until we obtain a fully liquid profile and we only have liquid fat, for example, at 50 degrees C, we obtain the second part of the information. To obtain the solid fat content, we need to calculate the area of the liquid and the solid contribution. In the case of the liquid profile, this is rather easy. We only have a liquid contribution, and the liquid contribution in this case will be at its maximum. It will be 100%. On the other hand, if we will compare the liquid contribution between the sample at 50 degrees and the sample at 20 degrees, we will see that the liquid contribution has, for example, decreased to 75%. In this case, we also know the solid contribution, because of course we know that the amount of solid and liquid fat are interrelated. In this case, we obtain a solid fat content of 25%. To illustrate to you the strength of this SAXS technique, I would like to show the solid fat content of palm oil as determined following the AOCS method. First, the fat is heated at 100 degrees, then it is cooled to 60 degrees, cooled to 0 degrees, and then heated to its final temperature. In this case, the profile was recorded both with NMR and with SAXS, and as you can see from the graph, the result is clearly very reliable, and it really resembles each other. On the other hand, if we would like to analyze a suspension, it becomes way more difficult. In this case, the black line is the reference line, so it is the solid fat content curve of the plain palm oil. For the purple line, we also use the AOCS method. So again, we heat it to 100, we cool to 60, we cool to 0 degrees, and then we cool to the final temperature. But we use the suspension that contained 50% of palm oil and 50% of sucrose. In this case, you can still see that the solid fat content of the palm oil and the palm oil suspension is related to each other. It is not too much of a difference. On the other hand, we would like to study suspensions as they are. So if we want to do an isothermal crystallization, which is more industrially relevant, for example, we would like to keep the sample first at 70 degrees and then isothermally cool it to another final temperature. In this case, what we obtain is the blue curve. This blue curve has clearly a higher solid fat content than the solid fat content for the plain fat. This is of course logical because of course when we add the sucrose, we add a large amount of particles, we add a large amount of surfaces to which the palm oil can adhere and to which the nucleation will be enhanced and the crystallization will be enhanced. This graph clearly displays that we cannot just use the solid fat content of a plain fat to mimic the solid fat content of a suspension. To conclude this presentation, I would like to recap why we would like to study the solid fat content via small angle X-ray scattering. Because first of all, the solid fat content of a plain fat is not necessarily the same as the solid fat content of a suspension with this fat. Secondly, SAXS allows to study pre-crystallized suspensions and ready-made products. And thirdly, small angle X-ray scattering allows to follow the sample during continuous isothermal crystallization. To end this presentation, I would like to thank you all for your attention and thank the FWO for the research funding. Thank you.
All right, thank you, Fien, for an excellent presentation. Now we have 7 minutes of Q&A from the judges and the audience. I'd like to remind the audience to enter your questions into the chat.
Okay, maybe I will go ahead and thank you, Fien. Excellent talk and very interesting research. I know that, SFC by NMR is a standard protocol and you are trying to use a novel technique. I wanted to know if you can tell us a little bit about the fundamentals of why the SFC curve gives a peak for solid fat and a flat for liquid fat. What's the reason behind that? The fundamental of how small angle X-ray works, I mean, and the signal that coming out?
Well, small angle X-ray, well, it is in one sense comparable to a synchrotron analysis, and in one sense it is of course not. We have a source of X-rays that hit your sample, and what then happens if when you have a structured lattice that has recurrent distances between different atoms, for example, or in small angle case, larger distances, like for example, the lamellar spacing for fats, then this X-rays will be scattered into a certain direction, which in that case obtains you with a 2D profile. And that 2D profile can then be integrated over an angular range to obtain the 1D profile that I have shown. The small peak, so the peak from the solid contribution, it comes from a very fixed length, which is coming from, of course, your lamellar spacing, so from the length of your fatty acid molecules. So a 2L or a 3L distance. For the liquid fat contribution, of course, there is some material present, but the order in this material is way less. So what we produce there, of course, is a broad bump of your liquid signal and not a very specific peak. The same holds for a wide angle scattering study. Also there we have more narrow and defined peaks for fixed lengths in a polymorph, and we have a broader bump for the liquid fat that is present, just because there is less structure into the material. The same would hold, for example, for a particle that is amorphous versus crystalline. Amorphous will always yield something which is a broad bump.
Okay. On a related question is, so you said the fatty acid length will change the peak position. So this is palm oil, and if you use coconut oil, do you think that you need to calibrate? I mean, the peak will shift to a different Q values? I mean, can you tell us a little bit?
Well, indeed, I am not very familiar with coconut oil, to be honest. But depending on your fatty acid profile, of course, and especially the way how your fatty acids are posed on your triacylglycerol molecules, because we are not sure, for example, that the short fatty acids together will form a 2L and the very long ones together will form also a 2L. That could cause, for example, that we obtain, in the ideal case, two distant peaks for our 2L. Very short, very broad. On the other hand, that is never the case. We always have like a separate distribution, and that causes the peak to broaden. So the more narrow the fatty acids length, let's say, in the distribution of your fat, the more narrow your peak will be. And the wider the distribution of the fatty acids, for example, in milk fat, there is a very wide distribution of fatty acids. The peak will always be wider.
Okay, thank you.
You're welcome.
Hi, Fien. This is Tiffany. Very nice presentation. Thank you very much. Question regarding in regards to emulsions. Do you think SAXS could be applied to evaluating the solid fat content of a oil and water emulsion based on your experience or some of your work you've done?
I think so, yes. It will be possible, but of course, the more difficult part with oil and water emulsions is that the amount of solid fat rapidly decreases because there is less fat present. And of course, for a laboratory device, this is one of the main issues. That the lower we go in fat content, the lower we go in solid fat content, and the more difficult it becomes to distinguish between what is noise and what is actually a peak or a bump coming from the liquid profile. It also depends how we can solve it in some ways. For example, we can take multiple profiles and add the intensity one to another. But also depending, for example, if you want to follow it during isothermal crystallization, for example, of course, we want to take multiple measurements over time, and then it is more difficult to mimic such a situation. But in the ideal case, yes, it is possible to study.
Okay, thank you.
Hi, Fien. This is Christina. That's a very good presentation. I do have a question regarding the impact of position of fatty acid chain on the SAXS peaks. So, for example, look at fat or triglycerides has a different fatty acid chain in 1, 2, 3 position, how this going to impact your peaks, like liquid part and the solid part, how this impact your peak position and your peak shape?
Of course, if we would have an ideal case and we can mimic very pure triglycerides and obtain a fat like that, it would be more easy to study. But in general, we are not aware of, in a plain fat, how are the exact peak position or how are the exact positions of the fatty acids on the triacylglycerol. And even if we would know that, it is indeed very difficult to study which triacylglycerols align with themselves in peaks, for example. It's, for example, also known that the lamellar structure is formed before the actual polymorphic structure or the subcell packing is made, which makes it even more difficult to derive that. And if we would have like triacylglycerols that have all the short fatty acid chains together, of course, we would form a very short 2L distance. And then we could again separate into 2 peaks in the ideal case. However, on a laboratory scale, this is more or less impossible because the peaks, they are broadened by the fact that the source is not ideal, that the intensity is not super high. But in general, if we would change only a minor fraction of the fat, we would not see the result on a lab scale SAXS. Not in the way the peak is positioned and not in the way the peak would be broadened, yes or no.
Okay, great. Well, we're all out of time for questions. Thank you so much for your excellent presentation, and we'll move on to our next speaker in just a moment. All right, welcome back to the AOCS ePoster pitch competition for the Edible Applications Technology Division. Our second presenter is Lingyi Liu. Lingyi is a PhD candidate in the Department of Food Science and Technology at the University of Nebraska, Lincoln. And the title of the presentation is Microstructure Controlling on the Printability of High Oil Paste Formulated with Nanoporous Starch Aerogels, or NSAs. Take it away, Lingyi.
Hi, everyone. I'm Lingyi Liu from the Department of the Food Science and Technology, University of Nebraska, Lincoln. Today, I will present an improved work of 3D food printing with nanoporous starch aerogel. So, first question, so what can 3D printing bring us? Besides the keywords I listed on the screen, let's do some imagination. So every morning when we go outside, before we go outside for the work or the school, we set up the food material in the kitchen and take out our smartphone, open an app if we have one, and choose our preferred recipe, processing method, and set the starting time. When we finish the work and get home, we will see the food ready to eat, probably in a very interesting and attractive shape, like the dino shape on the right photos. If I can give my daughter this, the food like this, she's a picky eater. She can eat almost food I give to her, even the vegetables she doesn't like. So that's a good vision for the future of 3D food printing. But unfortunately, now we couldn't do that because we are still facing a lot of challenges because this technology is at a very early stage. One urgent problem is that we have limited choice for the printable food materials. The extrusion-based 3D food printing is the commonly used one. And for this technology, the food material should be easily extruded out of the tiny nozzle and also display their strength to support the dilated layer by layer structure. Now, most of the research focuses on the hydrogel-based or the starch-based material. In our previous work, we established a model printing paste containing the high content liquid oil to broaden the potentiality of the application of 3D food printing. But one remaining problem is that for the design shape-wise, if we don't place the printing paste for 24-hour storage, the printed shape will collapse during the printing. So that's the problem. We want to solve it. And the nanoporous starch aerogel is the solution to this problem. In our lab, one method has been developed to produce this porous nano-scale material by using the supercritical dyeing method. And we can see after the starch aerogel production, the surface area can be greatly improved. And considering the big improvement in this aspect, we suppose it can help us to improve the printability of our modern printing paste. We did it. Even we reduced the ratio of nanoporous starch aerogel to 1/3 of that of the corn starch, and the printing paste was still good, and we didn't need to put the paste for the 24-hour storage. And since it's the high oil content printing paste, so we also measure the oil leaking area to reflect the oil controlling capacity. We can see the oil leaking area has been greatly reduced by the incorporating of starch aerogel. To figure out which kind of factor are most significant ones related to the printability and the oil controlling capacity, the rheological property and particle size distribution were analyzed. We can see the viscosity and the storage modulus are significant related to the printability. For the oil controlling capacity, the particle size and distribution were the most significant factors, since a smaller factor can form the tighter microstructure, so it can help to reduce the oil leaking problem. So here we can make the conclusion. The nanoporous starch aerogel can improve the printability and oil controlling property. The application of nanoporous starch aerogel can reduce the particle size, narrow the size distribution, form the tighter microstructure, and increase the strength to support the dilated structure. Overall, the nanoporous starch aerogel can be used as a novel material in 3D food printing. So that's all for my attention. Thank you for your time.
Great job, Lingyi. We're now ready for the Q&A from the judges. And I'll remind the audience that if you have a question, please enter it into the chat function of whichever app that you are watching this from.
Tom and Christina, please go ahead with your question.
Sure. Yeah. Thank you, Lee. That's a very interesting presentation. So I do have two questions for you. So first question, can you just give a little bit of information about the equipment you used for the 3D printing?
Thank you for your question. For this question, I used one kind of the extrusion-based 3D printing. And for this device, we will have the syringe. and the put ink, or I call the printing paste in my project, and we put the printing paste into the syringe, and then there will be a pistol, and the pressure of the pistol and the printing paste will exude out of the tiny nozzle. And for that nozzle, we can choose a different size. It depends on the printability, your shape you are designed. And during the printing, there will be a motor connected to the syringe, which will moved and with the XYZ direction, and then can help us to shape the design shape.
Good. And how you dry your food? Like after this printing is done, do you need to put it in the oven to dry, or is any special drying process?
Yeah, that's a good question. So it depends on the application for the food material. For the printing paste in my project, we haven't dried it. We just put at the room temperature to observe the physical stability or the oil leaking area. But if we want to eat, the food material should be dried or should be heating processed. And at this time, probably we will adjust the ingredients and to make it more edible.
Okay. One more question is related to the sensory about the 3D printing the food. How do you expect it the pasta you made from the 3D printer compared with the current pasta from the regular process?
Yeah, that's the exercise we would like to do in the future, but unfortunately we haven't do that. We hope that because for this project for the aerogel we produced, and we hope the sensory, the tasting, and it could be normal or feel better compared with the current pasta, but currently we haven't do that.
Okay, great. Thank you.
Lingyi, very nice presentation. Thank you. Question regarding measuring the total oil content of your final 3D printed materials to ensure you're getting the right delivery of oil. Have you done any extractions, or how are you quantifying that you're delivering the right amount of ingredient or oil in this case?
Hi, Dr. Ciftci. Thank you for your question. Yeah, for the oil leaking problem, we measured by using we will take the photo at a different time after the printing. And then we will measure the leaking area by using the MGG. We calculated, because we can set the skier and then calculate the area by using the MGG software.
Okay, thank you.
Yeah, I have some question too. Very good presentation, very interesting research. I am a bit confused about how did you prepare the mixture of protein, starch, oil, water? Are you making an emulsion? What's the structure of that material? Yeah,
we can consider it's kind of the emulsion, because we have to use the whey protein isolate to mix them all together. If there is no protein, the paste we will see the phase separation, but it's more like the solid. It's like the solid paste stator. Yeah.
So did you use any homogenizer to mix? How did you mix all of this thing together? Just a blender?
Yeah, just the blender. We didn't use any other homogenizer, just mix the 4 ingredients together.
Okay, but so if it's a solid paste, how did you measure particle size of that paste?
Yeah, we will, for the particle size distribution, we will pick up around the 25 milligram samples and then dissolved in the 25 milliliter water, and then to homogenized and then measure the particle size.
So what are you actually measuring in particle size? Are you measuring oil droplet or starch particle?
We were measuring the paste sample, not the particle, the overall ingredient.
Overall particle size? Okay.
Yes.
And my last question is, so aerogel versus cornstarch. So when you have the aerogel, did you grind it to make it a powder and then use that? So if you grind it, will it still hold its nanoporous structure? How would that material look like?
You mean how the aerogel powder looks like?
Yeah, like cornstarch powder versus aerogel powder. I mean, how they are different?
For the appearance, I think the aerogel powder looks for the appearance, the color, it will be whiter, and then you can feel it's much lighter. The density is much lower than the starch. Yeah.
So even in powder form, it still has air incorporated in the structure, microstructure. In the nanoporous starch, nanoporous aerogel, even in powder form, it still has air incorporated. That's why it is more fluffier, lighter, right?
Yes, when we mix them together, it will be a little fluffy, but yeah, so we have to mix it very carefully.
Okay. Thank you.
Thank you.
All right, thank you to all of our judges, and congratulations again to our speaker. We are out of time and I did not see any audience questions, so we will move on to our next speaker. Thank you.
Probiotics have been shown to have several health benefits, such as heart health, digestion, and improved immunity. However, probiotics are very sensitive to various elements, such as processing, storage, temperature, and pH. As a result, the food industry needs improved systems to protect and really stabilize the probiotics in foods to improve their functionality and viability for consumers' health. Hello, my name is Rycal Blount, and the purpose of my research is to develop an oleogel-emulsion delivery system for probiotics. So oleogel-emulsion is a process that converts liquid oil into a gel-like material without really changing the chemical characteristics of the oil. And emulsions are a mixture of two or more liquids in which one is present as microscopic particles distributed throughout the other. So my materials for this research included using soybean oil as the dispersion phase and beeswax as the primary oil gelator or oil structurant, in combination with either ethylcellulose, monopalmitin, or glycerol monostearate. Oil gel emulsions were prepared with 3 different emulsifiers, and these were phospholipon, tween 80, and soybean lecithin. For the methodology, there were 6 primary methods of analysis and characterization that included the oil binding capacity test, OBC, visual tests, texturometer analysis, differential scanning colorimetry, also known as DSC, rheology, and polarized light microscope imaging. These analyses were conducted to understand the physical properties of the oil gel and the oil gel emulsion samples. So looking here, table 1 is a comparison chart, and it showcases where 100 ml of soybean oil is prepared in a 10% ratio with beeswax and either ethylcellulose, monopalmitin, or glycerol monostearate. Probiotics, again, are very sensitive to high temperatures. Therefore, my primary goal was to create a stable oil gel with a solidification point between 45 to 50 degrees Celsius for probiotic viability. This chart indicates in the yellow box that you see, the oil gels prepared with beeswax and glycerol monostearate in ratios 7 to 3, 5 to 5, and 3 to 7 had solidification points in our target range of 45 to 50 degrees Celsius, with very high structural stability as indicated by the OBC on the right-hand side. For the emulsion analysis, we chose the oil gel with the 7:3 ratio because it showed the best result with a solidification point of 45.6 degrees Celsius, and of course, high oil binding capacity. Oil gel emulsions were then prepared and tested with 3 different emulsifiers. Again, phospholipon, soybean lecithin, and tween 80, at percentages of 0.5, 1, 1.5, and 2%, along with 3 ionized water percentages, 5, 10, and 15% respectively. So for this characterization, it was the same for the oil gel analysis. This next slide represents the emulsion texture analysis. So the phospholipon emulsion that you see on the left-hand side at 1.5% phospholipon, as indicated by the green box, has the greatest consistent toughness and firmness out of the phospholipon sample set. The increase in water content from 5 to 15% increased the phase separation within the sample, leading to reduced stability. This is apparent with the emulsion at 0.5% in the red box, which had the least firmness and toughness and increased phase separation, particularly at the 10 and 15% water percentages. Looking at the right, the tween 80 emulsion results, as seen in the green box, indicate that the emulsion with 0.5% tween 80 with 10% and 15% water content had the highest toughness, firmness, and stability or spreadability out of all the emulsifier tests. And this included both the phospholipon and lecithin. But I will say that in the red box at 1.5%, that had the most consistent toughness and firmness. Furthermore, lecithin emulsion sample set had reduced firmness and toughness when compared with tween 80. However, it was noticed that the increase in water content did not reduce this texture strength, but improved it. And you can see that as the graph trends upward. So the conclusion of this research is that oil gels prepared with 7:3 ratio between beeswax and glycerol monostearine and 10% oil gelation show the desired temperature range from 45 to 50 degrees Celsius for probiotic viability. The increased water content did cause increased phase separation within each emulsion sample set. However, this does not always correlate with a reduction in oil gel emulsion structural stability and firmness. Furthermore, oil gel emulsions with 0.5% tween 80 at 10% water content has the most significant potential at being a probiotic delivery system due to its stability at the desired temperature range. So thank you very much for your time and attention, and I'm ready for questions.
Thank you so much. That was our third and final speaker, Rycal Blount. Rycal is a master's student in food and nutritional science at North Carolina Agricultural and Technical State University. So we'll now open it up to the Q&A. As a reminder, our fourth and final speaker had to withdraw, so this is our last Q&A. After the Q&A, the judges will take some time to deliberate, and the audience will have an opportunity to vote. And the directions for voting should be in the chat box. So judges, go ahead with your questions. And if your audience has any questions, just add them to the chat.
Tom, go ahead.
Yes, Lingyi, very nice presentation. Or excuse me, I'm sorry, Rycal. In regards to the toughness measurement, can you explain based on, is that using the texture analysis when the probe pulls up from the gel?
Yes, sir. Yes, sir. So you'll have a baseline sample container, and as the probe presses into the container, it's giving us that firmness and that toughness. And as it pulls away from it, it lets us know the spreadability. And so that lets us know overall those structural components of the sample. Yes, sir.
Thank you.
Thank you for your question.
And you notice the again with the, what's your theory around why the gels formulated with a lecithin may have had less firmness, less and more softer kind of gels? Let
me make sure. Can you repeat your question?
Yeah, with you indicated that with using soy lecithin, the toughness was reduced, the firmness was reduced. Any theory as to why lecithin created a softer gel or a less hardened gel?
Yes, sir. Well, as far as the theories, we are still in the process of reviewing the literature. It was surprising to see that over all of our samples, as we increased the water content, the strength of the sample was reduced. And so that had been the trend, but lecithin was the outlier, where as we increased that water content, that strength increased. So what we're doing right now is going in review process to really break down those chemical characteristics to better explain why that's taking place. So I can't answer you as of right now because we are still breaking that process down, but we are answering the question in process.
Thank you.
Maybe I can ask a few questions. Thank you, Rycal. Really interesting research. So if I understood correctly, you are making an water in oil emulsion, right?
Yes, sir.
And you are trying to deliver the probiotics in the water droplets.
Yes, sir.
But so far in the research, you haven't done work with probiotics, right? Just emulsion you are developing.
Yes, sir. So that is the second phase
of course.
Testing. Yes, sir.
Yeah. So when you are making a water in oil emulsion, typically an emulsifier people use that will tend to make water droplet. Twin 80 is really well known for its ability to make oil droplet. So Twin 80 is a typical oil in water emulsifier. So did you really look your oleogel emulsion under microscope to see whether you are able to form water droplets?
Yes, sir. So what we used was the polarized light microscope, and we were able, of course, for the time that is allotted to us, we can't go into every component. But when we looked at the 7:3 ratio with just the oil gel as it relates to the emulsion, we saw great stability and a really fine crystal structure that was homogeneous throughout the sample. And this is what we were looking for as a delivery system. So yes, we were able to see the fat and the water droplets, and it further proved that that ratio was really, really a strong supporter as a delivery system. So yes, sir, we did look at it from a microscopic perspective.
More than the ratio of oleogelator, I'm interested how Twin 80 are able to form water droplet. Because, one of the reasons that if you increase water, your gel strength decrease, could be that the water droplets are not very stable. But lecithin, maybe it is able to make water droplet properly, so maybe its gel strength is increasing. But obviously, that's an hypothesis. I mean, you are still working, I know.
Oh, no, yes, sir. I agree.
Yeah.
I agree.
My last question is, so now if you want to deliver the probiotics, people need to digest it and get the probiotics out of the water droplet. Now, beeswax is not digestible. Do you think that would inhibit delivery of the probiotic?
I would say that would be a component that we would more than likely test later. I don't think that it would inhibit it greatly because our digestion process, it's so tough in that regard. But I will definitely look into that and look at what other analyses that we can add in addition to like the oxidation, in addition to, of course, the probiotic testing that can give us a better answer as to what that would look like. But that wasn't a component of our direct research.
Okay, thank you.
Hi, Rycal. Thanks for your presentation. It's very interesting. I have one question for you. So for your oleo gel-based system, did you measure the stability of the whole system?
Of the oil gel itself?
Yeah.
Yeah, yes, ma'am. We looked at the oil gel, and of course we were looking at it with the texture, with the rheology, with the melting point. And so it was in those initial stability testings that we were able to decide what was our primary candidate to move forward with the emulsion testing. So yes, ma'am, we did look at the stability.
Okay.
Great. Okay, well, we have time for maybe one more question, and we do have one from the audience. And their question is, can you give more information on the phospholipin?
Phospholipin. Okay. Yes, that is what we wanted to look at, were different emulsifiers in the sense of like the fat components and how that would distribute throughout the sample. So I want to make sure I'm understanding the question correctly. Did they give any additional information as far as what their question is asking? And we chose our emulsifiers based off of what we have seen previously done. For example, glycerol monostearate was used as a substitute or fat substitute in meat packaging and sausages. And so we chose phospholipin and glycerol monostearate and ethyl cellulose, of course, based off of previous studies that have been done and how they might operate within each system. So if they give any further clarity, I hope I can answer them accordingly.
I think that was the extent of the question. So I think you answered it to the best of your ability. So hopefully they can approach you at the AOCS meeting, either in person or through the online website to further get answers to their questions. All right,
Okay.
so thank you so much for your great presentation. I believe that since that was the last presentation, that we're going to open it up for the judges' deliberation and for the audience poll. The audience vote occurs only on the AOCS annual meeting websites, and the instructions on how to vote should be posted in the chat function. We'll be back in a few minutes. right, so the judges and the audience poll has been tallied, and we're ready to announce the winner of the AOCS ePoster pitch competition for the Edible Application Technology Division. So the, sorry, just going to read. The first place winner will receive a $200 cash prize, recognition certificate, and a complimentary 2023 AOCS student membership. And our second place winner wins a $100 cash prize and a recognition certificate. So with no further ado, our runner-up for the competition is Rycal Blount from North Carolina A&T State University for her presentation, oleogel-based systems for delivery of probiotics. So congratulations, Rycal.
Thank you.
All right. And our first place presentation was Fien De Witte from Department of Food Technology, Safety and Health, Ghent University in Belgium, for her presentation, Determination of Solid Fat Content in Plain Fats and Suspensions with Lab Scale SAXS Device. Congratulations, Fien.
Thank you.
Congratulations to all the presenters and the winners. So well done, guys, all of you.
Yes, congratulations to all of the presenters. You all did a really great job. I'm really impressed. I look forward to watching all these presentations or seeing them in person at the AOCS annual meeting. And I also want to thank all of our judges for their time and excellent judging job. And I want to thank the AOCS Foundation for funding the competition and thank the audience for coming to this event and participating with your votes. So thank you, everyone.
Thank you. Congratulations. Great job, everyone.